So this is week 5 of our Dynamics on Networks class. Welcome back. As always, I need to remind you that this class is live streamed and recorded. So today we're going to continue our discussion of enzyme kinetics. And I'm hoping that we're able to get through some basic computational exercises and then do a little bit of mathematics associated with the basics of enzyme kinetics. If you've had courses in chemistry, some of the math will be familiar, or mathematical biology. If not, it doesn't hurt to review it here. And we'll talk a little bit about some basic Python that we're going to use. This is probably the most finicky thing in Python that we'll do is how to manipulate arrays in Python. There are a lot of ways to do that. I tend to use a sort of an old-fashioned one. And then I'd like to talk about Michaelis-Menten kinetics and Hill equations, which are the two basic approximations that people use to deal with complex reactions. And at this point, I'd ask people to start beginning to look at later chapters in the textbook. The material that we'll cover in the class isn't exactly in the order in the textbook. There isn't always a perfect linear order for things. And so there'll be bits and pieces of chapters 4, 5, 7, 12, and 14. 4, 7, and 14 are the ones that we're going to be focusing on immediately, because they're topics like parameter fitting that have to go somewhere but don't have a natural, and there's no particular reason to do parameter fitting as chapter 6 versus chapter 8 or someplace else. So I wanted to talk a little bit about the homework, but a couple of comments. First, I've said before that it's okay to submit revised homework assignments, especially if you try a homework, there's material in it we didn't cover that we covered in class and you want to submit again, where you've been able to do more material, that's great. But if you're going to do that, please do one, mark the assignment as as revised, and also let me know. So send me an email that you submitted a revised one, because Canvas doesn't always tell me when there's an uploaded new assignment. And 2, within the homework, if it's long, please do mark, problems 1 and 4 are the way they were, but problems 3 and 5 are new. So please indicate what you changed, so that when we're regrading it, actually when I'm regrading it, because we don't have an assistant, I'm a little more efficient at doing that, because I want to make sure if you do that, that you get the credit for what you've done. All right. And also, please do remember to upload your Jupyter notebook for computational problems. And in the homework, if it asks you to describe what you saw, please do screenshot the images of the outputs of the Jupyter notebook, so we can have that. I realize that takes a little bit more time, but if I ask you to describe what you saw, and you say, I saw this, if you don't have a picture, it's a little bit hard to follow. So please do that.
Can't you draw it?
If you want to draw it by hand, that's okay too, but I think it's usually faster to snapshot your simulation up. I mean, one of the things that's rather nice about Jupyter notebooks is that in principle, it's not the most convenient way in the world, but you could put text into a Jupyter notebook. And so you could actually have a Jupyter notebook essentially be a project where you type the text. The only problem is that formatting in Jupyter notebooks, you could do equations and things, but it's not so convenient. It's a little bit less convenient to do it. But do please put that in. If you have trouble doing the uploads, I know some people didn't figure out how to upload their PowerPoints from last week into the Canvas. So if there's ever an issue with a homework submission in Canvas, email it to me. And I've got a folder in the Google Drive for student homeworks where I keep everything. And so you don't have to submit it through Canvas. To get your grades, I have to fill out the grade in Canvas. But if you send it to me separately, as long as just make sure that I acknowledge it so it doesn't get spammed. But as long as you send it to me one way or the other, I can deal with that. All right. Any questions about that? We'll go over that a little bit more. As I mentioned, often I will ask you to explain what you see, and we'll have a class where we'll talk a little bit more about what that may mean, because that's a sort of a dangerous question to say, what do you see? What do you describe what you see? Well, I have no idea what's important and what isn't. How do I explain? How do I understand that? And one of the things that I hope we'll do in this class is begin to develop intuition about what kinds of things are interesting to ask about these kinds of systems. But I did in homework 2 try to give you some guidance when I said, if you're looking at a time series, what are some of the questions you could ask about it? Well, does it start at a value of 0? You don't have any of the chemical, or some non-zero value. Does it increase all the time? Is it monotonically increasing? Does it decrease monotonically? Does it go up and then down? Those are things that might be significant from a biological perspective. At the moment, what we're doing is sort of abstract chemistry. It's not really grounded in biology. And we're doing things that way really to get you the methodologies as quickly as possible. But when we start looking at real biological problems, then these kinds of questions will be more important. If we run the thing for a long time, does it go to a finite value? Does it go to 0? Does it blow up? And then if we're comparing things, what are we interested in usually? Relative values, relative slopes, relative times. Biology is all about differential measurements. Is something faster or slower when we do something else? Is it bigger or smaller when we do something? We give somebody a chemotherapeutic. Does the tumor get bigger or smaller? Those kind of questions. And so if we have 2 time series, A and B, is one increase faster or slower than the other? Is the final value at long times bigger or smaller for one or the other? If it goes up and goes down with a peak, does the peak happen before or after the peak for something else? Those are the kinds of things that you might look for. Now, I understand that if all the curve does is go down exponentially, there's not that much you can say about it. But pretty soon we'll be dealing with situations where we have more interesting behaviors. And so it's not a bad idea to start thinking about how to describe these. And then very often we'll be changing a parameter, and then we want to understand how all of these things change as we change that parameter. And there's a comment here that I'll come back to, which is when you're doing these simulations, we'll typically say arbitrarily that the simulation runs from time 0 to 10 or 0 to 5 or 0 to 20. But you have to develop some intuition about looking at that and asking, is that a reasonable time scale over which things happen? If everything happens in between times 0 and 1 and you run to time 100, you can't see anything. If time changes in the simulation are very slow and you run over a time scale of 10, you may not see anything either. And so you may have to adjust the time axis of your simulation to be appropriate for the simulation you're running. And that time that you need to run over may depend on parameters. In fact, it generally will. And so you have to develop a sense of what's a reasonable time frame to look at. William.
Well, with developing that sounds like that's something that I was thinking about. It's pretty subjective. You just do it until it sort of depends on what you're looking for in the graph, right? Or you do it until steady state or something, or until you see equilibrium or
so William,
time, you know what I mean?
Right. So William asks a very good question, which is, what is a reasonable time frame? How do you know what's a reasonable time frame? And he asks, should you be looking, for example, till you reach a steady state? Well, if the system does reach a steady state, it's not an unreasonable marker to use. And so you might ask the question, how long does it take to reach a steady state? and then go out maybe 20% beyond that for your x-axis. On the other hand, you might have a situation where what you really care about is what happens at very short time scales, because something strange happens over very short time scales. That happens with the enzyme kinetics that we were looking at last week. And in that case, you might want to zoom in and look just at that early time. And so absolutely, you're right that you have to adjust what a reasonable time means, depending on the kinds of questions that you're looking at. It's not a bad idea to start out by running a simulation over quite short times and ask, is there something interesting that happens over short times? And then run a second simulation where you go to equilibrium or steady state and approximate that. And for most of the things that we're going to do, those are really the two regimes we care about. If you have things that are chaotic or oscillatory, or things take a long time to equilibrate and then something happens in the middle, then there might be situations which they're more, you have to do some time window in the middle of the simulation. But in general, for these simple situations that we're dealing with here, that's not going to be so much the case. But that's a great question. Okay. So the next problem I was going to ask about was, I wanted to come back to this homework problem, which I think we went over a bit last week, but some people found this one confusing. It was a tiny bit of a trick question. It wasn't meant to be. There were two very parallel questions. We had this simple driven reaction where we had A going to B, just one molecule of A going to one molecule of B. And then there was a slightly more complex one in which we had 3A going to 2B, and we assumed that we had mass action kinetics. And I asked, what are the rate equations for A and B? And if we do this, we can read them off. A is created here by K1. It decays with KFA cubed. It's created with the back reaction KRB squared. And then we have to remember the stoichiometry, and that's always the thing that's a little bit tricky. So the stoichiometry says that we don't multiply by 3 when we have the K1. That's that sort of confusing arrow notation for boundary species. So we have dA by dt is equal to K1. For each molecular reaction, we lose 3 molecules of A, so minus 3 KF A cubed. And we get 3 back from the back reaction, 3 KRB squared. For the second one, the balance terms now don't match because we have 3 A's turning into 2 B's, so we have 2 molecules of B created for each reaction. We lose 2 molecules for each back reaction, and then the decay again doesn't have a 2 in it, it's just minus K2B. So that's that funny convention. And so you have to be, yeah, William, go ahead.
Wait, no, sorry, just to be sure, so you said going in at 2KFA cubed, and you're saying there's 2 molecules of B created.
Yes.
So
we destroy 3 A's and we create 2 B's. Now the reason this, if I weren't using mass action, it might be less confusing, because this 3 in front of the A and the 3 in the exponent are related to each other. That's from mass action. Where you might not expect it is because there's a 2 here in front of the B, you might expect a 2 here. But in fact, the exponent here, the 2, comes from the rate, but this numerical factor of 3 comes from the stoichiometry. It's just the fact that there are 3 A's. Similarly for B. And so you can think about this as a little matrix where the vertical ones come only from the rates, and the horizontal ones come only from the prefactor. And it's easy to get confused about that, but it is mechanical. If you're systematic about it, it works. And you'll notice it if you if you make a mistake, you'll notice that the thing won't behave in a sensible way when you run it. And so that was, I think, not a tricky question. But the second question was, what's the steady state of this reaction? And that's the one that some people got a little bit confused about. And so the first thing I want to do is just color code the reaction, and we'll talk about balance. Every time we destroy our A, we create a B. And so this minus 3 KFA cubed turns into 2 KFA cubed. And we have 3 KRB squared balancing minus 2 KRB squared. When we had just A and B, all we had to do was add these two to cancel out those features. In this case, we don't have to do very much more than that. All we have to notice is that if we multiply the second equation by 3 halves, everything cancels. And that was the trick that I think some people didn't get. And so what I'm going to do is I'm going to first set my A equation to 0, K1 minus 3KFA cubed plus 3KRB squared. And then the second equation, I'm just going to multiply by 3 halves. That gives me 3KFA cubed minus 3KRB squared minus 3 halves K2B star. And now I'm going to write one on top of the other. And now I notice that if I simply add the two, all the things with the cubes and the squareds disappear. And so it's easy to solve. So I add them.
Not to solve one first for A and one for B.
No, you solve B first.
B first.
Yeah. Elmer asked, well, should we solve A or B first? And so you solve B first because B gives you a simpler solution.
Because or is there a reason?
There is a reason. You have the same terms in the first and the second equation, so it's simpler to cancel them out. And what's left?
What was is B because B is there. Yeah,
The only term that lasts. So
right. The other thing to remember, which we covered last week. So Elmer is asking why do we know to do B first? And last week we solved this equivalent equation, and what we noticed was that for B, the amount of B depended on K1 and K2, but not on KF and KR. So it fundamentally was a simple result. Didn't care about how much A we got. And so we know from that experience that actually in a reaction of this kind, the last term in this cascade will be simpler. And next week, the homework, there's a cascade reaction where we have A goes to B, goes to C, goes to D, goes to E, goes to F.
Okay.
And if you do that kind of cascade, you'll find the same thing. You solve the last one first. It only depends on the thing that's coming in at the top and the decay rate. And then you take that last one and you plug it back in one layer up and you get the value for that. And then you plug that one in, back up, one up, and so on. So you build up from the end. So when you have a decay term like that, everything is controlled basically by that K2 at the end. If I were doing more of a math bio course or a biochemistry course, then we'd talk a little bit more about the math of that. If you're interested, a math textbook like Britain's Essential Mathematical Biology will cover that, or Murray Mathematical Biology will cover that, or that textbook, the Math of Life book that Connor likes so much, will cover that as well. Okay. So we add the two together and everything is going to cancel. I mean, another way to look at this would be if we look at these equations and ask, is there a way we can combine them that cancels out everything except A? The answer is no, it's not easy to do that. So that tells us to look for B. And we get 0 is equal to K1 minus 3 halves K2B. Before it was just K1 minus K2B star. And so now we get B star is 3 halves K1 over K2 instead of just K1 over K2. So all that's happened is that stoichiometry has given us the ratio if we destroy 3 and get 2. So nothing funny happens there. Now we have a value for B star. Now we plug V star back into that first equation and solve for A star. And this one is a little bit more messy algebraically, but it's no harder to solve. I have an equation which looks like 0 is equal to K1 minus 3KF A star cubed plus 3KR B star squared. And what we want to do is solve for A in terms of B, A star in terms of B star. Well, to do that, I put the A onto the left-hand side. 3KF A star cubed is equal to K1 plus 3KR B star squared. Divide through by 3KF. A star cubed is equal to K1 plus KR 3KR B star squared over 3KF. Take the cube root and then plug in B star is 2/3 K1 over K2. A star is equal to K1 plus 3KR times 2/3 K1 over K2 squared over 3KF all to the 1/3. Well, that's algebraically a little bit of a mess, but it wasn't hard to solve. I didn't have to use a quadratic formula or a cubic formula or anything. I just did simple algebraic manipulation. So if I know what K1, K2, KR, and KF are, I know what the value of A star is. So in general, if you have lots of reactions in a stack, they can get to be a bit more messy algebraically, but it's not a hard thing to solve. It's not necessarily pretty, but it doesn't require you to do anything complicated. It's not a difficult thing to do. Okay. And this is coming back again to this comment about time ranges. It's really a repetition of what I said before. And it's really coming back to the question that William asked, which is, if what you want to know is the final value, the steady state value, well, you've got to run long enough, you get to the steady state. If you want to know what happens over short times, then you need to do a short time zoom. And given that these simulations take a second or two to run at most, changing the time scale and seeing what happens a few times isn't that cumbersome. One thing that you sometimes do have to think about is that when the values change very rapidly, you may see that when you plot, you actually see things that look like steps. You see point, straight line, point, straight line, point. And in that case, you have to look at things like what's on the right here. We have simulate 0 to 5, and we haven't talked about that number, which is 1,000. But that number of 1,000 is saying divide the interval between 0 to 5 into 1,000 substeps. And so you may want to adjust that so things are pretty smooth. If things are changing fast, you'll need more steps. If things are changing slower, you can get away with fewer steps. And if you see discontinuous changes, you see jumps, everything we're going to work with in this class changes continuously in time. So a jump means something is wrong. I mean, in biology, the concentration of a molecule can't change discontinuously in time. Yeah, I guess it can come close. If you have a cell that lyses and suddenly releases a whole bunch of stuff into the environment, well, then the amount will change quite rapidly in time. But in general, in biology, things change smoothly. The other thing I wanted to talk about, and again, I understand that if you're coming from a computer science class or physics class or math class, the kind of open-ended questions about talking about things may not be so familiar. But for example, in the homework, there was the online resources, and perhaps I should have broken these out into a numbered list. But people were great about, I think last week, people were great about presenting their ideas and their papers, and they dug into this. But I gave, for the online resources one, I gave a list of possible questions to answer. And to some extent, these were perhaps I should have been more explicit that I wanted all of them answered. But I was hoping that it would be also guidance for people to think about problems. So if you're talking about, say, a library of networks, you might want to talk about what are its advantages and disadvantages. It attracted your attention, so what's good about it? Is there something wrong with it? Why don't people use it more? Is there some? A lot of people did talk about whether it's only on network architecture, also has reaction rates. Are the networks downloadable in some form, or do you have to retype all of it? And then those kind of questions, or describe the shape of the steady state curve. And so it's, I understand that it's tricky in the sense that it's not easy to develop a sense of what's enough of an answer for these questions. I'm certainly not expecting you to write 20 pages of description, but something a little bit more than it's nice is helpful. And so I'll try to give you some guidance of questions, sub-questions to ask and answer. But again, it's a little bit hard for me to do that in too much detail because I don't know what you're going to choose. And so exactly what questions are appropriate to ask about it may depend on what you choose. And so another way to think about it would be maybe spend half an hour on the problem and think about what kind of things can you say about it, learn about it in half an hour. I'm not expecting people to spend days on one homework problem, unless you feel like it, of course. But and then a small thing, but please, if you're citing papers, give the full citation, author, journal, DOI. People have a tendency to just dump the title of the paper in. And these days, of course, you could probably find it from just the title, but some of these papers have very similar titles. So it's if you're in Google Scholar, you could right-click on the thing and it'll give you the citation. You could cut and paste it. So it really takes about 5 seconds to give me the full citation. It's just as a habit, it's better to always have that material with you. All right. So those were some comments on the homework. I'd like to come back. The last time we talked about chemical equilibria, and this is a little bit like the stacks that we were talking to before. If we have, even for very complicated reversible chemical reaction, there's still a single equilibrium constant, which is basically K forward over K reverse. And this is assuming Hill equations. So the whole thing behaves as if there were just a single component on either side. That one is used a lot in chemistry, biochemistry. It won't wind up being that important in the problems we're going to work on. So I don't want to spend too much time on that. But there's some interesting mathematics of that. Again, I want to come back to this concept of a steady state, what mathematicians call a fixed point. That's just the values of the concentrations of the chemicals at which the change of concentration is 0 in time. And we have to remember that there may be multiple fixed points for a different chemical, for the same reaction. Suppose that I have chemical A and chemical B reacting with each other. Well, if I need one molecule of A and one molecule of B to react, then if I have no A, there's no reaction. Similarly, if I have no B, there's no reaction. And so 0, A is a fixed point. A, 0 is also a fixed point. Not a very interesting one in that case, but it's there. And now I want to come back to where we were last time, and I'd ask people perhaps to you can either fire up Tellurium now, or we can do it in a few minutes. But we were doing this enzymatic reaction as our first non-trivial example. So we have a substrate, chemical S. It binds reversibly to an enzyme E, and the rate of binding is mass action. So it's Kf times the concentration of E times the concentration of S. That makes a complex, which has got the somewhat confusing notation ES. And I have the dot to indicate multiplication of the concentrations, because otherwise it's ambiguous. And that enzyme plus substrate can either react to release my enzyme, because by definition by default, if I have an enzyme, it's returned after the reaction is over, and a product P, or I can have the complex break apart and give me back my E and S, and that's the back reaction KR-ES. And the key thing here is what we call a conserved moiety, which is the total amount of enzyme, that is free plus bound enzyme, together is conserved. It doesn't change. And so E plus ES is a constant. We can call that E total if we like. If we started out with no complex, no ES, then that amount is just the initial amount of E, 0. But in principle, we could have something else. And it winds up that mathematically, the fact that there's some conserved quantity means that if we're going to solve the things analytically or numerically, we have to be a little bit more careful. And you'll see in some of the older code, there'll be this conserved moiety equals true in antimony in tellurium. These days, that's turned on by default, so you shouldn't have to do it. But if you don't do it, it's a question of actually how you solve these things numerically. And some of these things are solved numerically by diagonalizing matrices. And if you have a degeneracy in the matrix and you try to diagonalize it, you get there's a divergence. So it's a singular matrix. So you have to let the solvers know that that's a possibility. All right. So we ran that, and we got our chemical reaction, and we picked all of our rates to be 1. And what we saw when we did this is now you can see how I do with describing a time series. So what do I see? Well, if I look at longer times, I see the amount of substrate going down to 0 from its initial value. And it looks roughly like an exponential decay. It's not quite. And the amount of product going up and then saturating. And the amount of E plus the amount of ES is a constant, so that's not the sum isn't so interesting. But if I look more carefully at the amount of complex, I see the amount of complex peaks relatively rapidly. And if I wanted to be more careful, I'd see that this is a convex curve here. And then it decreases gradually to 0, basically on the same time scale that S disappears. And essentially, the reason I'm losing my complex is because I'm running out of S to react with E. So those are the two main things. We have a monotonic increase of P, we have a monotonic decrease of S, and we have a peak of ES that happens early. And that peak is asymmetrical. The rise of the peak is fast, and then the decay is slow. So those are all things that we could say just looking at this very simple reaction. There's one more thing that's interesting, which it really would be easier if I could zoom in a little bit. If I look at the production of P, and I zoom in at very short times, I'll see that the slope of the production of P at time 0 is 0. It's tangent to 0, and then it comes up. And so there's a tiny delay in the production of P at the very beginning, because it takes time for the complex to form, and I don't get any of the product until the complex is formed. And so there's an itty-bitty lag at the beginning. If I were to adjust this so that the rate of production of the complex, Kf, were slow, in other words, if I made Kf 0.01 instead of 1, I'd see that that little shelf here at the beginning was stretched out. And I'd see rather a different shape. It would be flat and then come up more slowly. And that's something that maybe is worth trying. If you have this running, you could try what happens if you make Kf much smaller, make it 100 times smaller. And you'll see that the final values of S and P don't change. The exponential decay of S and the exponential growth of P don't change, saturation. But that early time behavior will be radically different if you change that. So we were talking about the simulation here, of this simulation here. This is what I have. And now let me make that K forward smaller and run it again. Well, in this case, it really is going to take a much longer, so I'm going to have to stretch out my times. Well, maybe I was wrong. Maybe that doesn't control it. So you see what happens here. Let's see what happens with this ES.
Make the time. Do you have to scale the time by the amount you scale the?
Let's see what happens here. Yeah, but so William says I should really be rescaling the x-axis time by the rates, which is reasonable. But let's see what happens. See what happens if I make K reverse small. If I make K reverse small, everything gets back to basically where it was. I don't lose much. So that doesn't do much. And I make the decay rate, which is R, smaller. What happens to the shape? I make the decay rate much smaller, then effectively I'm in that quasi-steady state regime. So maybe I was wrong about that value. So you can play with this and we can see what happens. The other thing that I wanted to talk about is this idea of what we call boundary species. And specifically, we can force the concentration of any of our components to be constant, which in a sense makes some of the things less interesting. But here, we might want to say that, for example, what happens if the amount of substrate is held constant? And to do that, we put a $sign in the antimony. So if we put a $sign in front of the S here, then S won't change in time. It'll be forced to keep its initial value. There's some more notation here. I don't want to belabor this too much, but sometimes you'll see chemical reactions that look like E goes to ES and backwards. ES goes to E plus P, and they've basically forgotten to put the E plus S in. And the reason for that is that they want E also to be able to go back and forth to say E plus I. And if you had E plus S in that where the E is, you couldn't write then having it go back and forth to E I as well. There wouldn't be any consistent way of doing that. So this is a little bit like an abbreviation, like a contraction, like can't for cannot, where there's a bit of an inconsistency. And so if you see something like E goes to ES, and they didn't write the S, or E goes to EI, and they didn't write the I, then there is an implied assumption that S and I are boundary species with constant concentrations. And again, all I can do is let you know what the standards of notation are. I can't make them fun to deal with. So E goes to EI would be written E plus I goes back and forth to EI like this. E plus S goes to ES. Has same reaction, but those are shorthanded through E without writing out the plus S and plus I. I hope you won't run into things that are confusing, but when you're reading papers, you will find that notation. Herbert is careful and generally doesn't do that, but I can't promise everybody's okay. And so in that case, you can define the rate constants and pull everything out. I don't want to go into too much detail. You have a little homework problem about this. So if I actually then want to write the equations for E, I have to think about what's going on. E going to ES, mass action means that the rate for, let me come back for that. Maybe I should actually walk through that. Let's do this one. So E going to ES, the forward reaction. The S is unwritten, but this is E plus S going to ES. There's nothing written on the arrow. And if nothing is written on the arrow, the convention is you use mass action as the law. It's a little bit like trying to interpret Chinese characters, I think. And so that means that this E goes to ES is actually E plus S goes to ES at a rate KF times E times S. The back reaction is okay because there's no second term. So the back reaction is just KR times ES. Similarly, E goes to EI. The I is unwritten, and so I have KF times E times I. And the backward reaction is KREI. And then I have a decay term, ES goes to E plus P. That's just K2 times ES. And so if I put it all together, I have the total rate of change of E is, I lose it going forward here. I lose it going forward here. I lose it going forward here. I get it back when ES decays. I get it back when EI decays. And so there are 4 arrows pointing to E here. And that means there are 4 reaction rates. And actually, there's a 5th one, which we haven't looked at yet, which is ES going to E plus P. So there's an additional one coming from here, which I haven't written. William asked very reasonably, how do I know which rate laws to use?
Yeah, I think it must be used the context of the problem, right?
And so, yes, so the point of all of this discussion of arrows and conventions is that, as William says, it's got to be the context of the problem, but that's right. At some level, again, I will try to avoid, except in this particular homework problem, because Herbert frames this homework problem. I will try to avoid doing this to you. In other words, I will try to write, if I give you a set of arrows, I will try to have them all be complete. I won't ask you usually, except in an exercise like this to get used to it, I will not ask you to try to infer those things. When I write an arrow, you'll find that it almost always has a rate on top of it. And similarly, if it's E plus S goes to ES, I will write E plus S goes to ES. But then the problem is that I don't have any way of writing what's happening to E by itself, because E is participating in 2 different, it's actually participating in 3 reactions. The problem again is I don't have any way of, when I have the free E, I should have E plus S goes to ES, and I should also have E plus I goes to EI. And I have to write that as 2 separate lines. I can't put them into one diagram. because the E is doing two different things at the same time. I made a definition here, which is the rate at which I produce ES is Ks times E, concentration of E times concentration of S. That's mass action. But S is a constant. S is not changing. And so I can define Ks prime, which is Ks times the concentration of S. And then I don't show the S in the rate. And again, I'm afraid this is a standard contraction. It's a standard abbreviation. And so it won't look like a mass action rate because you don't see the S, but the S is there inside of the rate constant. So yes, I skipped this step where we define Ks prime to be Ks times S. And similarly, Ki prime would be Ki times I.
But what's the whole point of that? Simplify it down.
Well, somebody thought it would simplify it. You're not writing the S out. You're not writing S. You're writing a single number, a single rate. But you're right. You're hiding things in that rate constant.
Yeah. Well, which is like that, like you're going to multiply. You see K prime S, you're going to use Ks times S.
Right.
Okay.
Yeah, I don't find it a simplification myself. I find it making it more confusing. Again, I'm simply reporting the standards of the field.
Yeah. Okay. I got it.
But yes, I thank you for asking for the clarification. And I'm not this particular diagram that we're looking at here is actually one that you run into fairly common in biology. This is called competitive inhibition. And typically what you would do in a situation like this is you would ask, if I add I, it's called I because it's acting as an inhibitor. If I add I to my dish, does the rate of production of P go up or down? And the answer is, as I add more I get less, the rate of production of P goes down. And why is that? Because to produce P, I need the enzyme to bind to S. And as I add I, more and more of my enzyme gets attached to I and is not available to bind to S and to make the product. And so basically I'm sequestering my enzyme. I'm hiding my enzyme away so it can't react. And that's called competitive inhibition. And that's a pretty common biological regulatory mechanism. William asked, is there such a thing as competitive activation? There isn't really competitive activation. There could be cooperative activation, and we will come to that later today. There are other kinds of inhibition. For example, instead of having the I bind to E by itself, the I could bind to ES. So I could have a pair of arrows coming down from ES going to ES plus I goes to ESI, also a non-functional intermediate. And that's another homework problem. And that has slightly different, the effect of I on the production of P is somewhat different in that case. And so that also happens. But the key thing in both cases is that the I is taking E away from it doing its job and holding it somewhere else, sequestering it. Now for activation of receptors, transmembrane receptors, well, it's actually pretty similar. I can have a receptor on the surface of a cell that's sitting there waiting to bind to, say, a growth factor. And when it binds to the growth factor, it sends a signal on the cytoplasmic side. I can have a molecule that binds to that receptor, but doesn't trigger the signal on the other side. And basically that's clogging up my signaling pathway so that I don't get the signal. And there are a fair number of, for example, anti-cancer drugs that work that way. So that kind of competitive inhibition, here it's thought of as an enzyme kinetics, but it also shows up in signaling quite a bit as well. So this kind of diagram is one you may run into because it does happen pretty often, and it often is written with a shorthand. While we're doing this, one of the things that we might do, just to see what it looks like, and I'm not going to run for 1,000 steps because it's too long. Let me run for 100 steps. Is I'm going to print M, the result of my simulation. And if I print the result of my simulation, I maybe need to change the size a little bit here so that it works a little better. I'll see I have a sort of a complicated object, but my object is essentially a table, and this table has columns. And perhaps somewhat interestingly, the columns actually are named. So it's a table which has headers at the top of each column. So I'm actually allowed to refer to the columns of the table not only as column 0, column 1, column 2, but actually column time, column E, column S, column ES. And so I can actually ask for the values of ES. I don't only have to get numerical indices. And so but by default, the output of the simulation, the first column will be time. And then the other columns are all the variables in the problem, E, S, ES, and P. Because in my simulation, I had E, S, ES, and P. And I think the order is the order in which they're declared in the antimony string, although I've never checked that. I can find out. Let's try finding it out by changing the order here and see whether the column order changes. Yes. So William asked, remember that I said that there's a conserved moiety, which was E plus ES should be a constant. And he asks, how do we know that E plus ES really is a constant in our numerical results? Well, one thing, of course, that I could do here would be to go in and explicitly add ES and E and check that it's a constant value. The other thing that I can do, which I haven't talked about yet in antimony, is I could define a variable, say E total, and I haven't talked about the notation yet, but the notation colon equals, I'm sorry, I keep getting confused because the keyboard has these flip keys. I guess I never learned how to touch type, so I have to actually look at the key. E total colon equals, and now I'll make that E plus ES. And now I'm going to run it, and nothing changes, right? Nothing changes. Okay, so now you get to what I'm going to talk about on this. This is the perfect introduction to what I'm going to talk about on this slide, which is by default, antimony will output, tellurium will output in that table that we just looked at together. The first column will be the time, and the other columns would be the variables that are declared in chemical reactions. But there are other things that I might want to plot. I might want to plot the rates, J1, J2, J3. I might want to plot E total. I might, for some reason, want to say R is the same all the time and plot the value of R at every time. And so antimony has a very simple syntax for doing this, which is after, in my simulate function, I can put a comma, And then I can put a list, a Python list, so it's square brackets. And then I can tell it what variables or values I want it to output. And so now I can say, I want the first one to be time. Don't call a variable time. Antimony will get very unhappy if you call a variable time. It's a reserved word. The one that usually people get stuck on is gamma. The word gamma is reserved for the gamma function, and so you have to be careful about that. But now suppose I want E total. Okay, and now I'm going to run that, and now, William, are you satisfied?
Yeah. Yeah.
So now I can tell it which ones I want.
Yeah.
Or if I want that rate, J1, it'll give me the rate. And so it's calculating all of those extra ones. It's calculating all those extra ones, but it doesn't automatically output them. I have to ask it to output them.
Wait, what is J1?
Yeah, sorry, let me scroll up. So when I declare a chemical reaction like this, J1 is equal to this rate. Now, in this case, it's easy enough. I know Kf times E times S. I don't need anything fancy for that.
Yeah.
But sometimes those could be quite complicated functions. And so it might not be so immediately obvious to me what that should be. So anything that's given a name in antimony, I can display by asking for it when I do the simulate. Okay. Is that clear to people?
So if I wanted to map E total with all the other equations, I would have to add those in individually.
So yeah, yeah, you don't get it for free. How do you ask if I wanted to actually add E total to my columns? Can I just say add the E total and not declare all of the ones? And I'm afraid you're stuck. If you name any of them, you have to name all the ones you want. So you don't get that one for free. You could run the simulation twice and ask for without any specification, get all of those, and then run it again and ask for the only that one, I suppose. But yeah, in general, if you want to name them, you have to ask for them separately. And there's some other tricks of the trade that we won't cover in class, but that as I say, Herbert has that very nice online textbook for antimony and tellurium. And so there are a lot of fancy features that are useful under certain circumstances that I won't cover in class, but it's worth doing a little bit of digging to see if sometimes maybe there's a special feature that you want that's there. I'll cover the simplest things that we use the most frequently, but there are additional possibilities. Okay. So we've already done this, but why don't you try typing time, ES, and P here and see what we get. And in Jupyter, if you put in parentheses or brackets and open, it automatically puts in the close. That's fine, except if you put in something like a quote, a single one, and you only want to add one extra, and you type it again, it'll give you two more instead of one. So why don't we just try running that one? And here we'll get the amount of ES and the amount of P and time. And you can also here, for the first time, really see the time steps. So we said here we wanted the time to start at 0, end at 100, and have 100 subtimes. And the time stepping is a little bit odd, 0, 1.01, 2.02. And so the times are not incrementing by 1, they're incrementing by 1.01. And then not 1.01, but 1.0101. And that's because it's dividing things 0 to 100 because of the way Antimony counts things is really 99 steps. So it's got an increment of one more than it should. So I think if I do here, see if I do 101. Yeah, if I do 101 steps, then it actually does it by 100. That zero basis is a little right. Python loops don't run the last element of the loop, so that's what's doing that there. So if I want it to actually come out, the times to come out clean, I actually has to ask for 101 steps rather than 100 steps. Did people get that? Could people pull the times? Okay. It's also possible for me to ask for the column. If I have M and I look at M and I ask for the column, and see if I get the syntax right. You see, this is something where having the printout of the cheat sheet for Tellurium would be useful. I never remember if it's a square bracket or if it's a regular bracket. I think if I ask for M parenthesis time, yeah, that's right. So this is what I wanted to show. This is something I was going to show you later, but this is a good time as any to mention it. M is this array. And if it were just a pure array, like a numpy array, I would have to say, give me column 1, give me column 2, give me column 3. But because it's actually a table which has the headings, if I say, give me M square bracket, and then the name of the column, it will return the values of that column. That's pretty useful. So if I do M equals r.simulate for the whole thing, this wasn't in our slides, but I'm going to do it anyway. And now I say, give me the value of P. I have to actually tell it, let's see, does time work? Time works. Does S work? No. Okay, so I have to declare, if I'm going to ask for the column, I think I have to tell it that I want the column. Yeah. So if I want to use that column indexing on the output, I have to declare it in the simulate. Did that work for people? Were people able to print the array? Okay. So now what I'd like you to do is use that and take the code that we just wrote and generalize it a tiny bit to compare the results when you have S being varied and the one where you force S to keep the constant value. So you want to run this once where S is the way it is and one where you put a $sign in front of the S. And the question is, how are they different? Does that make sense for people? And to plot that, it's easier to do that plot. It's easier to do that plot with the when you're picking your columns. You may not want to plot all of the variable values. And you could do this in a couple of ways. You could basically take this code, duplicate it, and say, I don't know, E1, S1, ES1, and so on. One with a $sign or one without. inside one antimony string, or you could have two antimony strings, one with a $sign, one without. It's up to you to decide how you want to do that. So the question was, we can ask for the variables to be displayed, the antimony variables will be displayed from the Python layer through Tellurium. The question was, can we change whether S is a floating species or a fixed species, a boundary species, from the Python layer? And unfortunately, the answer is no. This was not something that was thought about in the original design of the language. There are limitations to what antimony can do in a simple way, and this is one of the ones that we're going to find is a little bit of an annoyance. The other one that you're going to find is an annoyance is that you can't make the stoichiometry a variable. So I can't, if I say that 3e plus s goes to es, and I want that 3 to be something that I change. So I want to say, what would it be if it was 4 or 5 instead of 3? I can't do that. I have to actually edit the string to make that work.
But you could, but I thought, can't you access like KF outside of the?
I can change KF, but what I can't do is I can't,
Like if
suppose
that's
suppose that I had this be 3e.
No, could you have that be like lowercase a and then stick a down?
So what I can't do is this. No,
Or no, like a times e. Can do
no.
that.
Well, in this field, most of these use a representation, an internal representation called Systems Biology Markup Language, SBML. And the limitation that we're facing here is a limitation in SBML. And so the packages that support SBML would be things like Copazi, Cell Designer. There certainly are others, but those are probably the two most popular ones. And they're going to face the same issue. Now I certainly could write a little bit of Python that would go in and change that number as the string, but that's pretty inelegant. So I don't have a great solution for that. And it's only for the stoichiometry that it's a problem. So, I mean, I'm going to solve this problem in a very brute force way by just duplicating my lines. And if people see, oh, there is a way to do the stoichiometry automatically, and I just didn't notice that there was an extension to the package, please do tell me, because it's certainly possible that I missed something. I mean, that's not very elegant, but it's see, I need EA, SA, PA, ESA.
This is a new equation, J3A.
What do I have wrong?
J3A.
Yes, yes.
AB instead of PA.
Oh, thank you. Thank you. Yeah, so that's pretty ugly, but should do it. And this has too many columns. And if I look at my plot, there are a lot of elements. And so in this case, if all I care about is the production of product, I forgot to put my $sign in, huh? So let me put my $sign for my S. Now I'll run it. I have too many lines here to keep track of. And really, the only thing I care about is the rate of production of products. So I'm going to have it output time P and PA. And now I can see the difference between the two. So I've solved that. I've solved that in front of you, but I'd like people to try getting that to work for yourselves as well. It's okay. You see at short times they're the same, and then in the case of P, I'm running out of substrate. And so the rate of production of P, when I don't fix the amount of S, is slower.
James,
Yes.
using the $sign, I can simulate a gene activating a reaction. The gene can be either 0 or 1, and I can set it from outside the model.
So Pedro asks, could you use the $sign to turn on or off to represent a gene being on or off? Well, the problem is that you can't really add the $sign. There may be, we can look in the manual, maybe there's a way to tell Antimony to fix a value that's normally floating. Somebody would have to look in the Antimony manuals. I don't know the answer to that.
You don't need that. You can initialize the variable as a $sign, and then you just change it from outside.
So Pedro says you can change the value of S $sign SA from outside, from the Python.
Yes.
And that's absolutely true. Yes. There's nothing that prevents you from changing the value of $sign SA from Python. There's really nothing that prevents you from keeping SA fixed by having SA not change in the reactions either. But then you have to do a lot more by hand. The $sign really is designed to give you a quick way of saying, if this variable is not allowed to change, how does my result change without having to do a lot of retyping? You just add a single symbol to it. Okay. But that's a good point. Yes, you absolutely can go in and say by hand, I can load my values here, and then I can say r.sa equals 10, for example. And I'll see now that I've changed the value of SA in my solution. So yes, I'm allowed to do that. So the difference between what I did the first time and what I did now is that if I look at what I actually wrote on the slide, it says set S0 equal to 10. And I ran it for S0 as 1 the first time. And if I make S0 10, over the time scale I'm simulating, I notice that they diverge very slowly.
Yeah, I guess it's the same.
Are they right on top of each other?
Yeah, I mean, I don't see blue. It's just orange.
Okay, so then try making S0 1 and see, then you should see the divergence. So William says that in his case, he's not seeing any difference between the two one with S held constant and one with S changing. Yeah, so the time that it takes for it to start diverging, the bigger S is, the longer it will take for them to differ from each other. Because effectively, if the rate of change of S is slow, it's only till when S is about 20% smaller than it started out, then you'll see a divergence. And so it takes a little bit of time for that to happen. So how did it work? If you excuse me, I'm going to stop printing the value here so we can see the plot in the same more easily. So this is when I start out with S 10, and after 100 time steps, not that much has happened. If I start out with S of 1, you see the divergence happens much more rapidly. So there's a question, which is, what does the work that we've been doing so far have to do with modeling cellular networks? And that's a reasonable question. At the moment, we're essentially learning syntax for the modeling language, and I'm giving you the syntax in simple cases, so that we can get familiar with the way the syntax works.
Yeah.
And then I will try to get us as soon as possible to doing things that are more interesting. And there's always a little bit of a tension, because I'm with you that I like the idea of getting to more complicated models quickly. The things that we're doing here, we will keep doing, but the rate equations will be more complicated, fundamentally, is the answer.
But so you're saying this is a node? We're in a node.
So when you see like one substrate, like
Yeah.
know the substrate, and when the network, then you have just many nodes, and they are interconnected to each other. So Biological network, and you really know the two maybe. That's how I.
Right. So I mean, suppose that we have, I mean, so for example, the formation of a complex,
Yeah.
and the formation of a product is something that happens inside of cells all the time. Now, here we're just describing that one enzyme plus one substrate goes to one product. Yeah. So if we were doing something that were more realistic, like metabolism, there might be 30 of those. But the fundamental form wouldn't look very different. There might be more components, but the way we write it would not be very different. And so again, I agree with you that what we're doing here is very simplistic. And one of the things that I think is a limitation of Herbert's textbook, and it has something to do with sort of how much one can cover in a semester starting from where we start, is that he doesn't have that many fun biological examples. He has a feed-forward network, he has an oscillator, he has a toggle and a latch. But those are the main circuits that he runs. That textbook of Oriolon's that I said Oriolon. Oriolon also has a textbook, but not the one but it's not the one. Mike Elovitz at Caltech, the one that I shared with you. He has some nice circuits about compensation and some other kinds of molecular circuits. Herbert has a nice review article on some basic motifs, which has examples in it, which we have a reference to. There's also a classic paper on biological motifs by Arkin and Ross, which has lots of nice examples. And so, again, I guess how to put it, what I'm trying to do in the class at the moment is teach you the basics of grammar and some vocabulary. And then I'm hoping that you could write some beautiful essays in the form of models based on some interesting biology. And so I'd like people, that's what I was asking people, for example, for a paper list. One of the things that we've done which has been sort of fun in the past, is to take a paper that has an interesting network in it. And then if there's 6 people, we might divide the class into 2 groups of 3 people and have each group spend the class taking that paper and replicating it in Antimony here in the class, and then working together to compare our results and help each other to do that. So if there's a paper that has a biological result that you think is interesting, I mean, if it's got hundreds of reactions, it's not going to be something we can do in 3 hours. But if it's something with 20 reactions, for example, cell cycle regulation, Tyson cell cycle regulation is something we can do in a class. Some of the viral replication and infection models we can do in a class. There's a hemoglobin model that people have done that you could do in the class. Trying to think of some other, the chemotaxis, bacterial chemotaxis and chemokinesis, key A, key B, you could do in a class. So there are lots and lots of biological circuits that are not really very hard to implement. In other words, maybe part of the problem here, and I don't want to take too much time because I want to keep going to get us to the more exciting fun stuff, is to say maybe one of the problems with Antimony is it's so simple that it seems like, why are we taking so much time to do things that are so simple? So if we should go faster, then maybe we should go a little bit faster. Okay. All right. So this is what I got for that simulation, where you have this slow divergence of the two with time. And so that's something that we could do. There's another little bit of Python that I wanted to cover today. And there are 2 commands. The outputs that we get from Tellurium are these arrays. And we often want to do parameter scans of various sorts. And so I want to talk about how to do parameter scans. And one of the things that Python allows you to do is to slice arrays, that is, pull out pieces of arrays. And it allows you to do these in rather complex ways. You have numpy functions that will find the row that has the biggest value, or the row that has the smallest value, things of this kind. You can have it return the mean, the standard deviation, many things like this. The syntax for array slicing can be a little bit tricky. You have lots of brackets, and remembering what order the brackets go in can be a little bit tricky. Another thing that you could do in Python is you can extend arrays and combine them in various ways. And so suppose that I wanted to change the value of the amount of enzyme, for example, and I wanted to know how the rate of production of P changed. And so what I'm going to do here is I'm going to run the simulation many times, and I'm going to keep track of the amount of P that's being produced as a function of time. And I'm going to assemble I'm going to change the value of the parameter, run the simulation, accumulate that new set of P values. Boy, P values is an unfortunate name, isn't it? If you're a statistician, the new values of P, and I'm going to keep adding them to an array. And so there are a variety of ways you could do that. One of the things that you could do is run the simulate function and just output the time to get that first column of the array, which is the times. And then I can run it again and again. And suppose that what I want to know is the rate of production of P. The rate of production of P, not the amount of P, but the rate of production of P is J3, or R times S, ES. And let me, I guess I could leave the other stuff in there for my code. I should probably clean it up a little bit. And so if I do simulate and I just ask for J3, that'll give me how fast P is being produced. And let me just run that one by itself. And let's see what that looks like. So I'm going to ask for J3. And I'm going to run it. I lost a per. Okay. And you'll notice here, I've got not enough. You see how it's jagged here? It goes up too fast and then it's jagged. That means I don't have enough time points. So I'm going to smooth things out. So you'll see the rate of production of P goes up very, very fast. And then it goes down very slowly over longer times. Let me zoom in. The rate of production of P goes up very fast and then gradually comes down. And now I want to know how that changes, how that curve changes as I change a parameter. What if I change the amount of enzyme? Or what if I change the reaction rate? How does that change? And I want to be able to overlay this. And one of the ways I could do that would be simply to tell it not to plot it and to overlay the plots individually. But instead of that, I'm actually going to assemble the data into a big array. And I'll show you how to do that. So I can run simulate once and get the list of times. And then I can run the simulation for J3 and get the list of J3s. And then I can use a method in NumPy called hstack. And what hstack does is it glues arrays together. I don't know how have people used hstack. There are other ways of merging arrays, but if I have array 1 and array 2, and I say array 1 equals numpy.hstack of array 1 comma array 2, and notice they're lists, so I have to put them in square brackets, then it will glue the arrays together, side to side. Now, if the number of rows in the array doesn't match, it'll fail. So you have to have the same number of rows. But this allows me to add as many columns to the list as I want. So I don't have to know in advance how many iterations I'm going to do. And so now let's actually write a little loop that will do this. The first thing I'm going to do is I'm going to create an array M, which just has my times, my column of times. And then in this case, I decided I'm going to change the amount of substrate that I have. I remember that I have to, when I'm going to run my simulations repeatedly, I have to keep resetting them. I'm going to reset my simulation. I'll make my value of S, my new value of S. I'll simulate it. I'll stack it. And then let's see what happens. Why don't you try that? Is this clear? Try that code. So what we have here is we do M equals R dot simulate 0, 20. Well, I made it 101 instead of 100 here. And the top one time. And that's creating the first column, which will have the times. And then I'm looping over S, and S is going to have the values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's going to stop at 9 because of the way Python indexing works. I reset my model to set time to 0. I overwrite the value of S with my new value of S. I simulate it for the same number of rows as before and get the rate of production of P. And then I add that to my array. I keep imposing that new array on top of the old array. And then at the end, which I don't have on the screen here, I do a TE plot array, which will plot my result. Okay. William, does that?
Yeah, it was down. Yeah.
No worries. Let's Okay. So to plot it, we can use a plot array. And then since we don't know what our lines are, again, the syntax isn't the most straightforward, but once you have done it once, it's easier to remember. It's relatively easy to remember it. So the plot array function has the ability to add labels. And so I can create a list of labels. There are a variety of ways I can actually do the labeling, but here I can do a list of labels. And so what I'm going to do is I'm going to create a blank placeholder for labels, which I'll call label. And this is going to be a list. And then the labels is a series of strings. And so each time I run my simulation, I can do it here. When I create the value of S, I can say label dot append. That's how I add things to a list. And I'm going to add S equals. And then it has to be the string value of S. And then when I do my plot array, I say labels equal label. And now when I run it, I get a key for my colors. So that syntax is not the most obvious, but why don't people try taking a minute and add that? You create a blank, an empty list where you're going to have the labels to put on your plot. Each time you run through your loop, you append to your label list a string which consists of S equals, and then the value of S, string of S. And then when you do your plot, you tell it to label it with the list of labels. I wouldn't expect people to remember the syntax of that. That's one of those ones which it's in the cheat sheet, and I always would just find some code which I already had working in and copy it. Again, there's some fancier ones you can do if you want. Okay. Another thing that we might want to do is ask the question, if we want to plot the steady state as a function of parameters. Here we're plotting a variety, well, his chair squeaks, huh? We're plotting the time series as a function of a parameter. But we might also want to change, plot the steady state. And so in this case, we're going to ask the question, what is the rate of production of P at long times? And it doesn't take very long because we see it saturates pretty quickly as a function of S. And so this is a question of, if we increase the amount of substrate for a fixed amount of enzyme, how does the rate of production of product change? Is that clear question? And in this case, we're going to have to fix the amount of S. And we'll also have to fix the amount of P, because otherwise the amount of product will go to infinity. So we're going to have to add some dollar signs. And in this case, we're going to use another numpy array manipulator. This one is not the most convenient one in the world. And again, what I would suggest doing here is just seeing it once, save it, and then copy it. One can look it up, and I certainly encourage people for things like this to try out ChatGPT or whatever your favorite LLM code generator is, and ask it for it, because it may very well know the manuals for Tellurium. In which case, if you say, please generate, ask in ChatGPT, please give me a parameter scan to do X for a Tellurium model, it may very well know how to do it. And then you don't have to remember these things. Instead of dredging your way through the NumPy manuals, it's sometimes much faster to ask ChatGPT. I certainly do that at home, so I encourage you to do it at home as well. So what we're going to do now is we're going to write a simulation where we're fixing the amount of S and fixing the amount of output P, just so that P doesn't blow up. And we're going to be calculating the rate of production of P, which is RES, as a function of S. And we're going to create a pair, which is the value of S, comma, RES. And we're going to sweep that, and we want to then plot that. And so now we have to know how to get that out of our simulation. And what we're going to have to do now is create an empty array in which we're going to put all of this information. And NumPy has a variety of ways of doing that, none of which are particularly easy to remember or friendly. In particular, NumPy has a concept of empty, which allows me to define a shape with no rows and no columns. It tells me what the shape is going to be, but doesn't put anything in it. Some languages let you do that, some don't. It's a sort of a slightly odd concept. And so there is a NumPy command called empty. And then what's a bit confusing about empty is you say shape equals, and then you need the number of rows and the number of columns in regular brackets. So William asks, what in the top of this, I have a little bit of a pseudocode here, which is what I want to do is I'm going to be changing the value of the amount of substrate.
Yeah.
And what I want to know is what is the rate of production of product as a function of the amount of substrate. And I want to make those in a pair because I'm going to plot a graph where the x-axis is the amount of substrate and the y-axis is the rate of production. Is that not making sense? People look either very tired or confused. All right.
But why the dollar sign?
The dollar sign is because I don't want the amount of substrate to be changing, because I want the amount of substrate. I say, if the amount of substrate is 10, how much product do I get?
That and then the value of substrate, like
Right. So the dollar sign is telling me that inside of my antimony, I'm going to put a dollar sign in front of the S. So my notation is, having just complained about all these abbreviated notations for the arrows, I've just done something like that here. So VStack allows us to combine arrays, not side to side, but top to bottom. So HStack adds columns to an array, VStack adds rows to an array. And so perhaps, unfortunately, the syntax for VStack and HStack isn't quite symmetrical. You would expect that since they're fundamentally doing the same thing, the syntax would be the same, but it's not quite the same. And so in this case, matrix equals numpy.vstack, regular bracket, square bracket, matrix, comma, what I want to add in square brackets. Now, this is if I'm going to add a single line. If I wanted to add a matrix, it would just be result 1, comma, result 2 would be possible. But in this case, I'm adding S, comma, value as a matrix itself.
Yes, because the first is an abbreviation, because it will first need the row and then you the column, but when you only write that, please indicate directly, so
Right, yeah, because I could have said array 2 equals S comma R dot J3, and then it would have looked symmetrical with the other one, yes. You're right.
yeah.
Okay, so let's try doing that. We're going to use matrix VStack to do this parameter sweep. And then we'll plot with plotArray. And there's a command in Antimony that is supposed to get the final result for a simulation, the long time result. It's called getSteadyStateValues. And I will tell you in advance that it does not always work. Sometimes it will crash. And if getSteadyStateValues doesn't work, then if you just run r.simulate for a long time, that will work. And so these days, I usually just run r.simulate for a long time. But this is an old slide, so let's see what happens. And you shouldn't need that conserved moiety analysis equals true anymore. That's older Antimony syntax. So let's try this out together. Let's walk through what this is doing. We're first telling it that there's this conserved quantity, which is E plus ES. Then we're creating a placeholder array in which we're going to put our results, which has 2 columns and no rows. Then we're going to scan S between a value of 0.1 and 9.9. We reset our simulation. We update our value of S. We try getSteadyStateValues. If it crashes, we'll just replace that with running it by simulate for a long time. And then we accumulate at the end of our array, our result, S comma rate, and then we plot the result. So we don't have to change that many lines here in our original code, right? So let's try that. The first thing we have to do is we have to put our $sign in front of S, and we're going to put a $sign in front of P, so they don't run away from us. And in this case, I better get rid of the stuff I'm not using. So I'm going to get rid of those lines that we created for the other code, clean it up. And now let me try that. I'm going to say, please try it yourself, follow along, see what it works. Result equals, and there are other ways of getting a blank empty array in NumPy besides this one that may be prettier. I often in these classes will have a student who's a much more sophisticated Python user than I am, and they'll say, "Oh, just do it this way." And so, if anybody has a cleaner way of doing these manipulations, that's fine. Okay, so I create my empty array. I'm going to iterate for S. And here I'm going to make S go from 0.1 to 10, and I'm going to make my step size much smaller now. These don't change. I don't need my label function anymore. And I'm going to try that r.get. Let's see if it works. Oops. Yep. Jacobian matrix non-invertible. So maybe I do need to have r dot conserved moiety analysis equals true. Oh well. Yeah. All right, that worked, except it didn't plot what I wanted. Oh, because I plotted M, not result. There we go. So again, what are we trying to do? We're going to run, change the value of S. And our question is, what is the rate of production of product as a function of the amount of substrate? And I realize that this may seem like a fair amount of fuss for the level of result that we have, but our result is actually going to be a very classic biochemical result. And so I do want to, it is worth going through this, I think, because it's such a classic result. Does anybody, if the alternative way of doing this, instead of doing this fancy stuff, is I could just do this.
But then you have to test if it's really steady state or not.
Well, I pick a time that's long enough that I'm confident that that's right. They both work. One of them is actually solving the equations to get the steady state value. That get steady state value is actually iterating to solve the equations explicitly. The other one as an approximation. The approximation one has the advantage that it'll always work. May not give you quite the right answer, but it'll always work. So I'll give people a few minutes to try to get that to work. And you should see something like this. And if you're stuck, the code is available in the student materials folder.
Wait, where do you put the $? Put it anywhere in front of an S?
So you need to put a $sign in front of an S and in front of a P. Because if you, it seems sort of funny to be constraining the amount of P, given that you're trying to determine how fast P is created. But if you don't do that, what will happen is that the amount of P will go to infinity. And so if you try to solve for the steady state, it'll fail because P will diverge. And so that's not a very pretty way of doing it, but it works. And it doesn't care where you put it. If you put the $sign in front of any S and any P, it will work. And if you look at the bottom of this slide, you'll see the name of this student materials folder is called Michaelis-Menten. And so when you do chemical reactions, the first chemical reaction that you learn, rate law that you learn is mass action, which is the rate of production is proportional to the product of the concentrations. The second one that you learn is Michaelis-Menten. And Michaelis-Menten is, in fact, the statement of what the rate of production of product is as a function of the substrate concentration. And what you'll see here is that the substrate concentration is the x-axis. For small concentrations of substrate, the rate of production increases linearly. For large concentrations of substrate, the rate of production saturates. And why is that? Well, if I have small concentration of substrate, my rate of production of product is limited by the substrate. I have plenty of enzyme. If I have an enormous amount of substrate, I'm limited by the amount of enzyme I have. I can't have more ES than I have E. And so there is a maximum rate of production that's limited by the amount of enzyme. And so in this case, for small concentrations of S, I'm limited by substrate. For large concentrations of S, I'm limited by enzyme. And Michaelis-Menten is a simple interpolation between those two regimes. Patty says she has a syntax error in the VStack where it says the number of arguments is not right. And so that usually means that some of your brackets are the wrong kind. You have one regular bracket and two square brackets. And it's easy to forget which is square bracket and which isn't. As I say, the worst thing in Python is at least the worst thing in Python for Antimony and Tellurium is the array manipulation. Just how do I select a column? How do I select a row? How do I put stuff together? And the reason I stick with things like np.vstack and hstack, you can also use appends and other kinds of things. The reason I stick with vstack and hstack is, while they're not elegant, I'm used to them. And so I've done them enough time that I know how they work. They're an almost limitless number of array manipulators that you have access to. And if you prefer different ones because you're a Python jock, that's fine. But the goal is the same thing, which is we want to build an array where we're adding rows to the array. And for people who got it, did you use the get steady state value option, or did you do the run for a long time option? Okay, so it worked for you. Which way did you do it? Okay, great. So you've got one vote for each method. Okay. So this is what we get. And now, if this were a homework problem, I would ask you to describe what you see. And so let me tell you what I see. What I see is that the rate of production of P, dP by dt, is an increasing function of the amount of substrate. The rate of increase is maximal when the amount of substrate is 0. So the slope of this curve is maximal at 0. And it decreases as S gets bigger. And if I made this go up to not 10, but say 30, what I would see is that it's going to saturate. It's going to go up to a maximum value. So it has a finite maximum for large values of S. And this shape is the Michaelis-Menten rate laws. And this is something again, in this class, I tend to try to avoid doing too much math. But this one is so important, and it's done in every math bio textbook. It's one of the things you do at the very beginning of a math bio problem. And so I am going to walk you through the derivation. I'll do it a little bit quickly because I don't want to run out of time. If people should feel free to ask if they're confused by it, or you can go to any of the textbooks, especially, I think, for example, Britain Essential Mathematical Biology has a good derivation. Frankly, Wikipedia, if you ask for Wikipedia derivation of Michaelis-Menten law, it'll give you the derivation as well. There are a couple of different approximations, ways of deriving Michaelis-Menten. One is called the quasi-steady state approximation. And in this case, remember that if the rate of production of product was small, then the rate RES also stayed roughly constant for a long period of time. And that's called a quasi-steady state approximation. And in the quasi-steady state approximation, we're going to assume that the rate of change of ES is 0. That basically the amount of ES is constant in time. And that makes life easy because the rate of production of P is R times ES. And so in this case, what we need to do is solve for the amount of ES. And so we now have to look at our equations, and we may have forgotten by now, but we have here the rate of production of ES is Kf E times S minus Kr ES minus RES. That was the rate of production of ES. And we're going to set that equal to 0. We're going to say that that's steady state. And now what we have to do is we have to get rid of what, if we look at this equation, we have 0 equals Kf E times S minus Kr ES minus RES. We want to solve for ES. We know S because that's the given. What we want to solve for this is as a function of S. And so the problem is that we have E and we don't know what E is. But remember that ES plus E is a constant, is E total, the total amount of enzyme. And so E at any given time is equal to whatever the total amount of E was minus ES. And so I can now replace E here by E total, which is a parameter, minus ES, and I only have ES's left in my equation. So I'm going to do that. And I'll be left with Kf times E total minus ES times S minus Kr ES minus RES is 0. So I'm going to multiply through here. I'm going to combine all the terms with ES, and I'll just do the algebra to solve for ES. So I'll collect all my, here I've multiplied through, and I have all my ES terms. I have ES times minus KFS. I have ES times minus KR and ES times R. And so I wind up with KF E total times S. It's the one thing that doesn't have an ES in it. Minus quantity KF times S plus KR plus R times ES. So now I move KF E total times S to the right-hand side, and I divide through by the thing in the brackets. And my result is that ES is KF times E total times S over KR plus R plus KF times S. And that looks like a bit of a mess, but KF times E total is just some constant. KR plus R is just some constant. And I can do a little bit of redistribution here. I could move the KF into the denominator. And so I get E total times S over KR plus R over KF plus S. And now I'm going to define a new constant, which is called the Michaelis constant, which is Kr plus R over Kf. And I'm left with ES is equal to E total times S over K Michaelis plus S. Well, this looks like S over constant plus S. What does that look like? If S is small, Km plus S is approximately Km. So this looks like S over Km. If S is big, the denominator is approximately S. So this turns into just E total. So if S is very large, this saturates at a value of E total. If S is very small, this is proportional to E total over Km times S. So I have the slope at 0, which is E total over Km, and I have the value for large S, which is E total. And so I have my function. So I don't know how people feel about a little bit of algebra. I hope that wasn't, I mean, I know after a long day of discussion, that maybe is a math is a bit much. And my feeling is usually math is better to do at the whiteboard rather than to show on slides, but I'm trying to walk you through the steps a little bit. Did that make sense for people? So the Michaelis-Menten rate law says the rate of production of product is V max, which is R times E total, times S divided by K Michaelis plus S. And K Michaelis, again, was given by this particular functional relationship of KF, KR, and R. And V max is given by R times E total. And that's the Michaelis law. There are a variety of ways you can rescale things depending on what you're trying to show. In particular, Km has the name of the of the half-maximal concentration. Km has the units of concentration, clearly because it's adding to S. If S equals Km, the rate is half of its maximal value. And so Km sets the concentration at which you go from having a rapidly increasing rate to the concentration at which you have essentially a saturated rate. So at the concentration S equal to Km is when the rate of production of the product is half of the maximal possible rate of production. People measure Michaelis-Menten laws in experiments. And this is from that nice physical biology of the cell textbook. And somebody did an experiment where they measured it for a simple chemical reaction. In this case, it's hydrolysis of ATP by myosin. And here you are changing the rate, the amount of ATP and looking at the rate of degradation of ATP for a fixed amount of myosin. And you get this beautiful agreement between the experiment and the predicted values. If that initial binding E plus S goes to ES is slow, then during that period, Michaelis-Menten doesn't apply. If you have a lot of sequential reactions, Michaelis-Menten doesn't apply. And when you have cooperativity, it doesn't apply. And so it's an approximation. It's an approximation when the formation of the complex is fast compared to the rate of degradation or production of product. And it's an approximation when the amount of enzyme, well, the amount of that there's only one rate, one stage of reaction. But as this experiment shows, there are plenty of biological situations in which it works pretty well. And so very often when people are asking for activation or inhibition in a signaling network or gene regulatory network. And you say, I know that the more A I have, the more FGF I get. The more FGF I get, let me pick one that's a real one. The more estrogen I have, the more MAP kinase I get. And I don't know what the functional relationship is. A first guess is it's Michaelis-Menten. As I increase the amount of activator, the amount of product that I get goes up, but it doesn't go up without limit, it saturates. And then the question is, what's the constant? And nice thing about Michaelis-Menten is that it has two parameters. I need to know what the maximal rate of production is, and I need to know the concentration at which the rate is half of its maximum. And so all of the possible complicated relationships I have are reduced to two parameters: the concentration at which the rate of reaction is half its maximal rate, and that maximal rate itself. And that simplifies life enormously, because in principle you could have all sorts of complicated dependencies, and in this case you can reduce all of those complicated dependencies to two parameters. So Elmer says Hill functions also have a half-maximal concentration, and in fact the Michaelis-Menten function is a special form of the Hill function. It's what you get when you set the Hill exponent to 1. So a Hill function has three parameters. It has the Vmax as Michaelis-Menten. It has the half-maximal concentration, Km, as Michaelis-Menten. And then it also has an exponent n. And if that exponent n is set to be 1, then you get recover Michaelis-Menten. Our initial reaction was E plus S goes to ES, goes to E plus P. Now suppose that our enzyme doesn't bind one molecule of substrate at a time, it binds n molecules of substrate. In reality, it probably doesn't do it that way. It probably binds one, and then it adds another one, and then it adds another one, and then it adds another one sequentially. But we're going to assume the first form. And we're going to assume then also that we have mass action. So the rate of E plus N times S goes to KF, goes to ESN, is KF E times S to the N. And this is the specific place where the fact that you can't make the stoichiometric coefficient a variable in antimony is a pain. Because I really would like to be able to write E plus N times S in my equations, and I can't do it. So that one I have to do by hand. That's the one thing I'd like to be able to vary in the stoichiometry. I can make the exponent change. The rate law, I can have the n change, but I can't change it in the stoichiometry. And I want to know what's the rate of production of P as a function of S. And so let's do exactly that. Let's take this exact equation here, everything we have here, and instead of saying E plus S goes to ES at a rate KFES, we're going to say E plus, let's use a number 4. And then we have to raise S to the 4. And our backwards reaction has 4 here. And nothing else changes. Is that clear what I'm doing here? Is it clear how the reaction diagram corresponds to what I've typed? What's changed from before? There's an N here that wasn't there before. There's an N here that wasn't there before. I've set N equal to 4. I get a 4 here, a 4 here from this end, and I have an exponent here of 4 there. What happens when you run it? So Elmer is asking, why is N and N here the same? And the answer is that I'm assuming mass action binding. And so if I have E plus 5s, then the rate of reaction is E times s to the 5th. If I don't care about the stoichiometry, if I don't care about the 4 here, if I just said E plus s has a rate EKF E times s to the n, and ignore the stoichiometry here, then I can make n change, and actually it's easier to do it as a simulation. But I'm doing this because this is really, from a biochemical point of view, this is the correct statement. Did it work for people?
Yep.
So let me see if it works for me. Well, I'm running it over much too big a range. Here, let's make it to 5. You get that? So you'll notice it's different. Now I have what's called a sigmoid. Instead of having maximal slope at 0, the slope at 0 is now 0. And the maximal slope is now at Km in the middle. Let's suppose that I don't demand that I have the stoichiometry. So I leave out, I don't care about the 4. Let me get rid of that 4. The rates are still correct, but I'm not using up 4 molecules. It's actually, if I run it, you'll see I can't even see the difference. It looks exactly the same. I now don't have a biochemical reason for the rate being what it is, because I don't have mass action anymore, but okay. But the rate is the same. Now I can scan, if I want, I could scan the value of n. And I'm not going to do that right now, but let me just do it by hand. Let me set r dot n. Actually, I better be careful here. I made this 4, actually 4. Let me make that n here. Here n is 1. So let me run this now. And this will give me Michaelis. N equals 1 here is Michaelis. If I make n equals 1, I get this. Let me now I'll just put this inside of a loop. I'll set 4. Again, I don't usually like the code on the hoof, but let's just see. 4 n in n pi a range 1, 10, 1, colon. So what am I doing? I'm going to loop over n here. And I'm going to see what the different shapes are as a function of that exponent. I called the array output n. So there we go. There we go. So now you can see the sequence as I change the value of the exponent. It would be more fun if I do if I don't display it at first, put it all in one array. There we go. Okay. Let's try this again. So what do you need to change? You need to take your existing code, and where you had E plus S, make it E plus 4S. Where you had E times S, make it E times S to the 4. when you have it coming back, make it E plus S goes to E plus 4S here.
Yeah.
Okay. And then just run it. Don't change anything
Yeah.
else.
No, I have that part.
Okay, good.
But-
So what you didn't get was the extra scan that I just did
Oh, I can't follow what you're doing.
I'm sorry that I shouldn't, I shouldn't do that. In other words, I shouldn't distract you. I just thought I was trying to jump ahead to remind myself how to do the calculation. And so let me just quickly do the same derivation that we did before. It's exactly the same derivation to get the result analytically that we did before. Except now, the only thing that's changed is that in our equation for ES, we have an nth power here. So remember what we did before. We said the rate of change of the complex is 0, approximately. The rate of change of the complex is KFE times S to the N minus KRESN minus RESN. We set that to 0. We distribute it so that we have KF times E times S to the N equals KR plus R ESN. And again, the rate of production is RESN. So this is what we want to solve for. And so now we have to get rid of E in favor of ESN, just the way we did before. So now we distribute KFE times SN over ESN is KR plus R over KF. This is our old friend, the Michaelis constant, or now the Hill constant. So we define the Hill constant, KH, is KR plus R over KF, and that's E plus S to the N over ESN. And there's one additional trick that we need. We're going to define K to be the nth root of KR plus R over KF, because we have this exponentiation we're going to have to get rid of. And so now we have E times S to the N over ESN is K to the N. This is what we want. ESN is equal to E times S to the N over K to the N. Why am I going to all this work? Well, I'm going to replace E by E plus ESN. E plus ESN is equal to E total. So now I put that into my equation. I have ESN is equal to E total minus ESN, that's just E, times S to the N over K to the N. Now I have to redistribute this to get that ESN over here so that I get my result. I multiply through. ESN is equal to E total times S to the N over K to the N minus ESN times S to the N over K to the N. I'm going to add ESN plus times SN over KN to both sides. ESN plus ESN times S to the N over K to the N is equal to E total S to the N over K to the N. I now distribute out ESN. ESN times 1 plus S to the N over K to the N, like that. And now my last step, I divide through by 1 plus S to the N over K to the N. And that's the Hill law. The rate of production, ESN, is E total times S divided by the scaling factor, the half-maximal scaling factor, raised to the nth power, over 1 plus S over K, again raised to the nth power. notice that if n is 1, that's the Michaelis function. And so this is written very explicitly because I now have something called a Hill function, which is e times x to the n over 1 plus x to the n. So whatever my s is and my k are, if I just divide s by k and plug it into that function, I get the Hill function. And that's precisely what I plotted here on the right, as it happens, for different values of n.
Can you show the model string? No, don't you need to? Oh. No, wait a second.
Okay. And as before, I define the maximum velocity as r times e total. And I'm left with the rate of production is V max, s to the n over k to the n plus s to the n. And that's the Hill function.
So don't you need to multiply the s by n too?
Sorry?
Don't you need to multiply the s by n too?
I just, yeah. So Pedro asked, shouldn't s be multiplied by n? So I explained earlier that the derivation of the rate law based on mass action assumes that that's true. However, the rate doesn't depend on that. So putting the n in front of the s, there's a technical problem, which is that I cannot do it in antimony.
Mhm.
However, it also happens to make no difference to the result. So if you're concerned about it, you can try running it this way, and then by hand going in and putting the n back, and then you have to do each n separately by hand, and you'll discover that the results are identical. Elmer says, well, you can go in and do string manipulation and character matching inside of the string and use Python character matching to overwrite this. Next time, I will talk a little bit more about the way Hill functions work. But we got through a lot today, I think. And these basic forms of Hill functions and Michaelis functions, we will use again and again and again, because the moment we start talking about signaling networks and gene regulatory networks, all of our rate laws are going to be Hill functions. And so the question earlier about William asking us, when can we start doing things? The answer is, once we have the Hill function, we can begin to do things. And so we've built up now to the fact that we have a rate law that we can use to do a lot. And so what I would ask you to do is please do homework 3 to consolidate the methods we've done here, so that everybody is sure that they can use antimony successfully, so we can go forward and do biology going forward. Pedro asks, why don't we use the hyperbolic tangent instead of the ratio of the exponential of the exponentiated value of s? The answer is that the two functional forms are very similar. If you're going to take derivatives, the hyperbolic tangent is easier to take a derivative of. If you are going to manipulate it in other ways, the Hill function is easier. Numerically, it's faster to evaluate the Hill function. And if you actually plot them on top of each other, they are very nearly identical. What really matters is the following. What really matters is at 0, the derivative is 0. At k max, the value is 1/2 and the slope is maximal. And at large values, the value saturates to 1. Both functions have the same functional form. One is symmetrical in the exponential on the x-axis. One is symmetrical in the linear values on the x-axis. And so basically, if I take the logarithm of s and plug it in, then I get the other one. So in practice, in biology, we almost always use the Hill function. And the reason we use the Hill function is that mass action gives us the Hill function. In other words, we didn't just pull this rate kf e times s to the n out of the air. It's given to us by the law of mass action. And so there is in fact a biochemical justification for using this rate law. And there are experiments in which you measure this, and this is what you get. Now, there are also chemical reactions in which you do get the exponential one. So which one is more relevant is going to depend on the particular situation. But in general, biochemically, this is the reaction law that works the most accurately. But the difference in the result between the two is negligible. And again, I think now that we have the basics, I think things will move a little bit faster. And I understand that in some ways things may move too slowly and too fast at the same time. They move too fast in one way and too slowly in another. But I wanted to make sure everybody's comfortable with the basics. If you can run these basic parameter scans, find steady states, well, these basic things, once you can do these things, we can do a lot. Because now we take our simple code, which has one or two reactions, and we replace it with something longer. But basically, the workflow won't change very much. We've got a basic workflow that we can now use to do much more biologically meaningful networks. Okay. So I appreciate people's patience and engagement, and I will see people back next week.